I want you to just picture something for a second. It's a Tuesday. You're making coffee.
Yeah.
And outside, there's this stream of high-energy particles screaming toward your kitchen window at, like, 1,000,000 miles an hour.
Which is, to be fair, a pretty standard Tuesday in the cosmos.
Right. It's a shooting gallery out there. And the only reason we aren't, currently dissolving is because Earth has this invisible force field.
A magnetic shield.
Yeah.
We've all seen the diagrams in our high school textbooks.
The ones with the big loops coming out of the North and South poles. Exactly. But here's the thing. I always just assumed we knew how that shield worked.
That it was case-closed science.
Yeah. But you brought in a paper today that suggests we might be completely wrong about the engine that's running our planet.
It is definitely not case-closed.
Mm-hmm.
For the last century, we've been running on a theory that, works well enough for Earth.
For us.
But it falls apart the second you look at our neighbors.
Mm-hmm.
In this new paper we're diving into, it argues that the source of our magnetic field isn't a slush of molten iron. It claims the Earth is hiding a giant ring of superconducting material deep inside.
A superconductor? You mean like the stuff they use on, MRI machines and quantum computers?
It's the very same.
That sounds impossible. I mean, don't superconductors need to be frozen? The center of the Earth is famously not frozen?
It is not. But before we get to the sci-fi engineering part, we have to look at the crime scene. Why do we even think the current theory is broken?
So the current theory, the geodynamo.
We call it the geodynamo, yeah.
Okay.
It was proposed way back in 1919 by a guy named Joseph Larmor. And the idea is actually pretty elegant. You take a conductive fluid.
Molten iron in the outer core.
Right. You add heat to create convection, and then you spin the whole thing.
The spin is crucial, right?
It's absolutely mandatory. The Earth rotation creates what's called the Coriolis effect, which twists those convection loops into spirals.
Okay.
And that movement of conductive fluid generates electricity, which in turn creates the magnetic field. It's a self-sustaining generator.
So the recipe is liquid metal plus heat plus spin equals a magnet.
That is the recipe.
So then, if that's the universal rule, every single planet with a magnetic field should have those three ingredients.
You would think so. And that is exactly where the trouble starts. Because we have a planet right here in our own neighborhood that breaks every single one of those rules.
Mercury.
Mercury. It's the smoking gun that suggests the geodynamo might just be wrong.
I was looking at the data you sent over on Mercury, and it really doesn't add up. First off, it's just tiny.
It's about, 14% the size of Earth?
Yeah.
So because it's so small, it cooled off billions of years ago. The consensus is that Mercury's core should be solid.
So no sloshing liquid part of the recipe.
Strike one.
But even if it did have some liquid, I mean, it's barely moving.
And that's strike two. Mercury spins incredibly slowly. It takes 59 Earth days to rotate just once.
So if you were standing on Mercury, the sun wouldn't set for months.
Basically, yeah.
Yeah.
And with a spin that slow, the Coriolis effect, the thing that's supposed to twist the fluid and make the magnet, is, virtually non-existent.
So by all the rules of the geodynamo,
Mercury should be magnetically dead. It should be a lifeless rock like Mars or Venus.
but it's not.
It's not. NASA's MESSENGER probe confirmed it has a stable global magnetic field. It's weak, sure, but it's there. And the dynamo theory has to do some serious mental gymnastics to try and explain why.
It feels like astronomers are just carving out exceptions. Like, the rule works, except for, all the times it doesn't.
That's often how scientific revolutions start, right? You spot the anomaly.
Right.
And Mercury isn't even the weirdest one.
Oh.
If you really want to see the dynamo theory struggle, you have to look out at the outer solar system. The ice giants.
Uranus and Neptune.
Right. So Voyager 2 flew past them in the late 80s and sent back data that just baffled everyone.
I remember looking at the diagrams and the notes. I mean, here on Earth, magnetic north is pretty close to geographic north. They more or less line up.
They're tilted by about 11 degrees on Earth. Close enough. But on Uranus, the magnetic field is tilted 59 degrees.
That's not a tilt. That's lying on its side.
It's massive. And on Neptune, it's 47 degrees. But the tilt isn't even the strangest part.
What's stranger than that?
It's the location of the magnet itself.
Okay, this is the part I had trouble visualizing. A magnet has a center, and it's usually the center of the planet, right?
In the dynamo model, it has to be the center. That's where the core is. But on Uranus and Neptune, the magnetic center is offset.
What do you mean offset?
On Neptune, the source of the magnetic field is missed the center of the planet by 55% of its radius.
Wait, hold on. Let me just process that. If we're using Earth as a comparison, that would be like our North Pole not being in the Arctic, but somewhere near New Orleans.
And the heart of the magnetic field wouldn't be in the Earth's core. It would be somewhere in the mantle under the Pacific Ocean. It's completely lopsided.
How does a spinning ball of fluid create a lopsided magnet? I mean, if you stir a cup of coffee, the vortex is always in the middle. It's not off to the side.
You hit the nail on the head. Fluid dynamics naturally want symmetry. To explain Uranus and Neptune with the dynamo, you have to invent these really complex, very specific scenarios where only thin shells of fluid are moving in these weird ways. It gets messy.
Okay, so Mercury's too slow, the ice giants are too crooked. But surely the theory works for Earth. We built it here.
It explains the now. It's terrible at explaining the then.
The history.
Exactly. We know from the rock record that Earth's magnetic field flips. North becomes south.
Right, we've had nearly 200 of these reversals in the last 83 million years or so.
But look at the timing. It's random. Sometimes the field is stable for millions of years. Sometimes it flips after just a few 100,000. If the dynamo is this consistent mechanical process driven by Earth's rotation, why does it randomly freak out and reverse polarity?
The dynamo theory just says, what, turbulence?
Essentially, yeah. Chaos in the fluid. But that's not really a prediction, is it? It's just a description of what we see.
It's not very satisfying. So we have a theory that fails on small planets, fails on outer planets, and can't explain the history of our own planet.
And that's where Jerry Z. Liu and his paper on superconductors come in.
This is a radical pivot. We're moving from fluid dynamics, liquids, moving around to condensed matter physics, solids.
That's the idea.
But let's go back to my first objection. You can't just say superconductor and wave a magic wand. Superconductivity means zero electrical resistance, and we get that by cooling things down to near absolute zero.
Right.
The inside of the Earth is thousands of degrees. It's literally hell. How can a superconductor even exist there?
This is where Liu applies what's called the unified theory of low and high temperature superconductivity. The core argument is about what actually causes superconductivity.
Okay.
We usually use cold to stop the atoms from vibrating, so the electrons have a clear path to flow without bumping into anything.
Right, it's like a clear highway.
Exactly. But there's another way to stop atoms from interfering with electron flow. Crushing them.
Pressure.
Extreme pressure. We're talking about the boundary between the mantle and the outer core. The pressure there is between 136 and 360 gigapascals.
I don't even know what a gigapascal feels like.
Imagine balancing 300,000 elephants on a stiletto heel. That kind of pressure squeezes the atomic lattice so tightly that the electrons are forced into a specific state. They pair up and flow without resistance.
So it's a similar effect to low temperatures?
Liu argues that under these conditions, superconductivity isn't an anomaly, it's a normal state of matter.
So if you squeeze the material hard enough, it turns into a superhighway for electricity no matter how hot it is.
That's the hypothesis.
Okay, let's assume I buy that. We have this material deep in the Earth. How does it turn into a magnet?
It goes back to rotation, but not in the dynamo way. The Earth spins. Centrifugal force pushes heavier things out and sorts materials. Liu suggests that these superconducting materials drift toward the equator over geological time.
Forming a belt.
A giant ring. A closed loop of superconducting material wrapping around the core.
I can picture that, a ring buried in the planet. But a ring isn't a magnet. A ring is just stuff. You need a current flowing through it to make a magnetic field. Where does the juice come from?
This is the part that I think is the most clever. The current isn't generated by the Earth.
It's not.
It's induced by the sun.
By the sun? Now you're losing me. The sun is 93 million miles away.
Think about induction. If you have a magnetic field and you introduce a superconductor into it, the superconductor reacts. It's called the Meissner effect. They usually expel magnetic fields.
Okay.
But during the formation of this ring, something powerful happens.
Is it like charging a battery?
It's more like casting a mold.
Yeah.
Imagine you have a pole sticking out of the ground. That's the sun's magnetic field passing through the Earth. Now imagine you pour wet concrete around that pole.
The concrete is the superconductor forming the ring.
Right. And the concrete sets. It hardens into a solid ring. Now, even if you remove the pole, the hole in the concrete is still there. It retains the shape.
So the ring remembers the magnetic field it formed in.
In physics terms, as the loop closes, it traps the magnetic flux. It locks in the solar magnetic field that was passing through it at that exact moment. And because it's a superconductor with zero resistance,
the electrical current just keeps flowing
forever
without a power source.
The current is the trapped memory. It doesn't dissipate because there's no resistance. It's a fossilized magnetic field.
That is, wow, that's wild. So we're protected by a ghost of the sun's field from billions of years ago.
In a sense, yeah. The ring becomes a permanent magnet, powered by its own lack of resistance.
Okay. This is a very cool story. But a good theory has to explain the things the old theory couldn't. Let's run the weird planet test again. Start with Mercury.
Easy. Mercury formed, the ring formed, and it locked in a field. Then the planet cooled down and solidified.
And the ring.
It just froze in place.
Yeah.
It doesn't need the planet to spin fast. It doesn't need liquid to slosh around. It's just a frozen superconducting loop buried in the rock, keeping that magnetic field alive.
So the fact that Mercury is a dead rock is irrelevant. The magnet is a fossil.
Exactly. It solves the Mercury problem instantly.
What about the chaos twins? Uranus and Neptune. Why are their magnets so crooked and off-center?
Think about that concrete ring analogy again. You have this heavy, solid ring carrying a massive current inside the planet. It's a gyroscope. It wants to stay stable.
Okay, right.
Now, something hits Uranus. We know it was hit by something huge because the whole planet rolls on its side. In the dynamo theory, the liquid core should have eventually sloshed around and realigned with the new spin,
Fluids adapt.
but a solid ring. It doesn't adapt. It's rigid. If a massive impact knocks the planet's crust and mantle sideways, the superconducting ring inside, being dense and gyroscopically stable, might just refuse to move.
So the planet tilted, but the magnet inside stayed put.
Or they tilted independently. Yeah.
Yeah.
You end up with the planet spinning one way and its internal magnetic ring facing another. That explains the 59-degree tilt.
And the fact that it's off-center. That New Orleans problem.
That's just the displacement from the impact. The core structure shifted relative to the mantle. The dynamo requires the field to be centered because the generator is the center.
But the superconductor theory,
It says, no, the magnet is an object. If you shove it to the left, the field moves to the left.
it's amazing how much simpler that is. You don't need complex fluid math. You just need a car crash in space.
It unifies the explanation. Earth, Mercury, Uranus, they all have the same mechanism. The differences are just about what happened to the planet after the ring formed.
But wait, if this ring is so stable, if it's a gyroscope that resists being moved, why does Earth's field flip so often? We aren't getting hit by planet-sized asteroids every few million years.
No, but we are hot. Earth is still geologically active. We have convection currents in the mantle and core, hot plumes of rock and metal rising up.
And these plumes can hit the ring.
They can disrupt it. Liu's theory suggests that violent convection can physically break the superconducting loop.
Like cutting a wire.
Exactly like cutting a wire.
And what happens to the field?
It dies. Instantly. The current stops. The shield collapses. This would explain those sudden paleomagnetic discontinuities we see in the geological record. The lights just go out.
That is terrifying. So
Yeah.
the reversals aren't a smooth rotation.
No, they're a reboot. The ring breaks. The field vanishes. Then, over time, the rotation of the Earth forces the materials back into alignment. The loop reconnects.
And when it reconnects it pours the concrete again.
Yes, it takes a new snapshot of the solar field. And here's why it flips. It all depends on when the loop closes.
When? You mean like time of day?
Time of year, seasons. Because of Earth's tilt, the angle of the solar wind hitting us changes between summer and winter. If the ring repairs itself in July, it might lock in north.
Then it repairs itself in January.
The angle might induce a current flowing the other way, locking in south.
Precisely. It explains the randomness. The reversal depends entirely on the chaotic timing of when the ring heals itself and where Earth happens to be in its orbit at that exact moment.
So it's not a clockwork cycle. It's a crash, a blackout, and then a restart that depends on the weather and space.
It really frames the Earth's magnetic field not as this permanent feature, but as a fragile state of equilibrium.
Which brings me to the big question. So what? We're sitting here trusting this shield. If the dynamo theory is right, it feels resilient, a churning ocean that's not going to stop anytime soon. But if this superconductor theory is right,
Then our shield is a physical structure, and structures can break.
if a mantle plume happens to rise up in the wrong spot tomorrow,
The circuit breaks, the shield drops, and we are exposed to the full force of the solar wind until the loop can weld itself back together.
and do we have any idea how long that takes? The healing process?
It could be centuries, it could be millennia. We see these periods in the record where the field was weak or chaotic for long stretches.
It really changes how you look at the ground beneath your feet. We think of the Earth as solid, dependable. But in this model, we're riding on a delicate electrical circuit that's constantly being battered by heat from below and radiation from above.
It makes the fact that we are here, protected and alive, feel a lot more like luck.
I want to leave everyone with one thought. We started this talking about how the ocean floor is like a tape recorder, showing us the history of the magnetic field. But if Lou is right, the Earth itself is a recording.
How so?
That ring down there is a memory of a solar storm from billions of years ago. We're protected by a snapshot of the ancient sun.
And if that ring snaps and reforms, the next snapshot it takes will be of a very different sun.
And our compasses might never point the same way again.
I think I'm going to go buy some stronger sunscreen, just in case. Thanks for taking us through this. It's a lot to process.
It's a fascinating new way to look at our world.
Stay curious, everyone, and we'll catch you on the next deep dive.